So in our goal here to measure variance, we're going to look at how data deviates from the mean. And so if we have a set of data, and I'm going to start drawing graphs a little bit like this. I'm not going to draw the bins as much as there's just some grouping of data that we have collected together, and there's some mean. And you can think about this being filled up with little points of data. So I can look at one individual data point, x sub I, and I can compare it to the mean. And so what we're going to talk about is the deviation. And so for a population, the deviation is an x value in terms of the variable of interest, where the x of one piece of data, the piece of data we're looking at, minus whatever the population mean is. And that talks about how that one piece of data deviates from the mean. And so this is a population deviation. For a sample deviation, we're still going to use the variable x. We're going to talk about the one piece of data and how it deviates from the sample mean. And so notice our difference in notation here, where this is the population mean, and this is the sample mean. And so we have a way of talking about how much each piece of data deviates from the mean of a sample or a population. Now, one of the things we will notice, and I'll show this more as we add it up, but for normally distributed things, or things that are semi-symmetric, each piece of data over here will have a piece of data over here, but one will have a positive deviation and one will have a negative deviation, but they'll cancel each other out. And so the deviations themselves tend not to tell about the entire collection of data. And we have to kind of play a trick with it to get some information out of it. And so I'm going to show you the formula. And when we're done with the chapter, I'll talk a little bit more about formulas. But for population, we'll talk about its variance. And we're going to use another Greek, V-R-I-A-N-C-E, populations. And remember, populations get Greek letters, and so I'm going to use sigma squared. And what we do is we take an uppercase sigma, this is a lowercase sigma, and this is an uppercase sigma, which means we add all of the deviations. So we go through each piece of data and we add the deviations and we square the result. So we square the deviations and sum up the results of the square of deviations. And we divide that by how many members there are in the population. And I'll show you how to do this, because remember, this sum thing here usually says that we're going to add in columns, right? Sums say add in columns. So we're going to need a column where that's the information we have on it. So I'll show you how we make these. Now the reason we use the sigma here is if I take the square root of this, sigma on its own, which is the square root of the variance, I'm going to take the square root of this whole side, oops, capital N, we've got a big capital N, and this is known as the standard deviation. And this has a way of measuring how much each piece of data deviates from the mean. Now, what's nice about this is, whatever my variable of interest is, let's say it's feet, this would be feet minus feet, feet squared, and the square root of feet squared is feet. And so standard deviations have the same units as the variable we measured. And so that's why standard deviations get used a lot. You'll find variances are very interesting things to calculate. Textbooks questions will ask a lot about the variances. I have a tendency in my work only to talk about standard deviations because I'm talking about things, physical quantities, and I want the units to be the same. But the meaning that we will get from these things translate fairly well between them. Now, this formula, notice, has regular n in the bottom for population variance. Now, what I'm going to do here is we're going to show you how to calculate one, and then we'll look at how we would get a sample deviation later. So let's get a population data and put it together. So let's put this into some steps here, because we want to organize things into columns for this to work for us. So what we're going to do is finding the population variance. And once you have the variance, you get the standard deviation by taking its square root. So the first thing that you will need is you need to find the mean of the data. And again, we'll write that the mean in symbols is the sum of every piece of data divided by the number of things. Now for each data entry, find the deviation. Which is x minus the mean. So you do this on each piece of data, and you get the deviation. Square the deviation, which is going to be the individual piece of data minus the mean squared. And then sum the squares, which is you take the sum of all the square deviations. Divide by n, the number of data elements, and this will be your variance. Or the data's variance, I should say. Might not be your variance, but it's the data's variance, right? And again, in symbols, we write this like this. Whoops, not a square root. Square root's the standard deviation. My apologies. And the variance is the sum of all the deviations squared divided by the number of data elements. And to find the population standard deviation, take the square root of the variance, which is the square root of everything we calculated before. Alright, let's put this into practice here. Let's use some data. Let's go back to those companies A and B that I had from the previous example, which is also in the book. So using Corporation A, let me get my data for Corporation A back here. It had 10 starting salaries, and we'll say this is a population. We'll say this is everything we can get. It's every starting salary for this company in a given year, and that's a population. It's not a sample. And we knew there were 10 data entries, so I'm going to write n is equal to 10. We also knew that the mean was 41.5. And these are in thousands, if you didn't recognize that when I was saying the starting salaries. And so our mean was 41.5. If we sum this up and divide by 10, we get 41.5. And so what we can do is, looking at each data entry, we can find the deviation. So we're going to go back up to these steps here. We found the mean. We're going to find, for each data entry, we're going to find the deviation. We're going to square it, and then we're going to sum the squares. So the best way to do that is to make a table. So I'll make a table of my x sub i's, which is each piece of data. All right, 41, 38, 39, 45, 47, 41, 44, 41, 37, and 42. So my data is now. And if I were to add this up, the sum of the x of i's is 415. And if I divide that by 10, I get the mu of the 41.5. And so now I want to do the deviations. I want to do xi minus mu. So 41 minus 41.5 is negative 0.5. 38 minus 41.5 is negative 3.5. 2.5 is positive 3.5. So I'm taking this number and I'm subtracting from it 41.5. So I get negative numbers when it's less than 41.5, and I get positive numbers when it's greater than 41.5. And let's see, 41, this is a negative 0.5. And this is 2.5. This is negative 0.5, negative 4.5, and 0. So I've taken this number and I've subtracted from it the mean. And that gives me this entire column. Now if I sum up just these, take a second, go on the calculator and you add all these up, you'll find this equals 0. And so this doesn't tell us much information. Individually, it tells me how far this piece of data is away from my mean. But I want to talk about the data collectively. And so what I want to do, which if we go back up to my steps here, right, step 3 was square the deviations. So I want to square each one of these. And so negative 0.5 squared, well, a negative times a negative is a positive. The negative 3.5 squared, well, a negative times a negative is a positive. And so notice squaring all of these numbers makes them all positive. That's the nature of our standard deviation, is it makes them positive. In fact, notice this one and this one are on opposite sides of our mean. They're equally on opposite sides of their mean, but their squares are the same. And that's the power of this technique, is it reduces this spread to a positive value, no matter which side of the mean we come on. So again, with your calculator, take these and square them, and you'll find you get this column of data here. And so now if I sum, whoops, I should have a square symbol here. If I sum all of the things I just squared up, I get 88.5. And so everything is spread about 88.5. Well, to turn that into a variance, I'll say that the variance is equal to, well, it's the sum. Again, I'll rewrite my formula over n. Well, we know that this sum now, because I add up this column, again, take your time, plug it on the calculator, add up this column, is 88.5, and my n was 10, and so my variance is 8.85, or approximately 8.9. And if I take the square root of my variance. .5 over 10, I get approximately 3.0. And so this has a standard deviation of 3. And so this is a way of talking about how far the data spreads out from the mean in a positive value. And so standard deviations will become our means, not the mean, but it'll become our method for talking about how wide the data is. And we'll look at this a little more visually. And so that is the population standard deviation. I'm going to take a pause here, and then I'm going to do the sample standard deviation.